We're now going to take a look at the warns block, the warnings block that's stored in the AFNI APQC HTML. One thing to note, first of all, is that actually the label here can have a different color and background than the rest of the QC section buttons here. What we do is we put the most severe warning, and you'll see that we have basically a lot of subsections that are reporting on different things that have been checked. There's different levels of warning that go along with each one, from none to mild and higher. And what we do is we take the coloration in a couple different regards of the most severe warning here and put it up here. So for none and mild, if either of those was the most severe warning, the color background would still be black and the text would just be either this light green or light pink. For medium and severe warnings, when there's at least one of those here, then we change and invert the background color. This background color reflects a medium level warning as our highest level warning. A severe warning would have a darker red color, more like that button. So already when we open up the APQC HTML, we can see that there's something that maybe we should be particularly interested in or worried about, as it were. So let's start taking a look through these different items. These are calculated and stored in large, well, there are a few different items here. Several of them are calculated and stored during processing by AFNI Proc, and then some are calculated at the end by the QC itself. And this is really one benefit for having your full single subject processing all done by a single tool that can accumulate these things and show them to you. And it can also draw from beginning and end data and compare or whatever it needs to do to check for warnings automatically. So all of these are things that we have found useful to check for, often for unfortunate reasons, because we realize that these problems occur in real data and we want to try to prevent them. So hopefully they pop up in pilot data rather than across all your subjects or something like that. All right, so the first thing we look for is mathematically when we're performing task-based analysis, as we've seen in a different lecture on general linear modeling and things like that. When we have regressors of interest, we need to make sure that none of those correlate very highly with each other or with other regressors of no interest or any linear combination thereof. That's called collinearity. And so we check for that because there's mathematics for how to do it. And in this case, there actually is kind of a medium level correlation between the visual and audio regressors. And if I just jump back up to the regress block here for a second, I can scroll down and we can get a sense of why that is. So this is my idealized response for the audio regressor and the visual regressor, the stimulus class of our two different tasks here. And if I tell you that you're in a period of time where there is, odd is off or 0, then you can almost be pretty sure that you're in a case where visual is on or nearly on in some way. And that level of interweaving between these, if one is off, the other is on, or almost, that's something that's not really done much anymore in task design data. So that's the medium level. In this case, the mild level warning here. It's not too bad, but it's something that could maybe be avoided. But anyway, so it's not torpedoing, but that's where it's coming from. The next item here is general sensor fraction warnings. So when we have in our AFNI proc command, what we did is we put in two options for censoring data, one based on a measured or estimated amount of motion, and the other based on volumes that have too many outliers occurring at that point in their time series. And so we can accumulate and count what fraction of our total time series across all three runs. So this is 400. We have 3 runs of 150 time points each that we're processing. So 6 time points were censored. That's 1.3%. That's not very much, and so that has just a no level of warning. So many studies have at least some motion in there for reasonable thresholds, and so this is not really problematic. What are the thresholds that we set for mild, medium, and severe? Are they absolute values that are set in stone? So if it's mild versus medium. These are just general guides, and you should always look at other aspects as well. But this is just to automatically check whether you have something like 15% or more, 20% or more of your time series are censored for motion, because often not only those censored time points are problematic or have disturbed data measurements, but often even ones that are below and subthreshold, they can have kind of lingering problems left over from that residual motion, as it were. So it can really be a problem when you have very high amounts of motion. So in this case, we don't. When we have task data in particular, we can check for another fraction of how much motion occurred. We can look at during the amount of time where an idealized response for a particular stimulus was non-zero, how much motion was happening during that stimulus. This is useful for knowing if, for example, maybe you only have a small amount of total motion, but for one of your stimulus classes, you have a very high fraction. In this case, that's not the case here, so it just so happens that there's 0% motion during the audio on time, and the motion tended to be only during the viz time, all 6 time points that we saw up above. If we look at this plot here, then we can, meant to look at the regress plot here. We can see that indeed during odd, when there's 0 here, that's when the censoring happened, and it was only when the visual was non-zero. So, okay, but these are not really problematic fractions. We still have a very large amount of data for all these stimulus classes, so we're not really worried about that. We're not also worried perhaps about stimulus correlated motion. That doesn't appear to be problematic, but as you have event-related designs in particular, or really any stimulus type, but when you have a very high fraction in a particular stimulus class, you're going to run into mathematical problems of trying to correctly model it and get a reliable result. But you also might need to reconsider your study design overall, because maybe the stimulus class or the way you're presenting the data or having the participant perform it is inducing motion, which really kind of cycles into a lot of problems. And so again, this would be something you would want to catch during the pilot part of your study, rather than having collected all your subjects. Okay, but that's not really worrisome here. We also check for whether there's pre-steady state in the data. So in this case, our data did not have pre-steady state time series. Actually, our data, our raw data, before we copy it in here, actually does have pre-steady state. And if I can just show this quickly in the, let's see, if I go up here, we can look at the raw data quickly just to see what pre-steady state looks like. I'll look at one run. So I just moved quickly to where the raw data is before processing. And as I click anywhere in the brain and I opened up a graph, if you see when I look at the time series in a little box here or anywhere, there's preferentially for every time series, there's a few time points that are higher, and then it settles down into bumps and wiggles. But it's not the same as motion, because some motion is up and down. Uniformly, the first couple time points are always, always, always higher than the rest. This is a hallmark of having pre-steady state. It's not a problem. It's just some scanners leave in the time series the time points where the magnetic field is kind of normalizing or reaching saturation for the start of the acquisition of data. Some scanners remove this automatically, some leave it in. And in our processing here, because the first couple time points, so if I hit the right arrow once, twice, we can see by this point we're kind of down in the regular time series. That's why during our processing, we left off the first two TRs of our data. They were removed when we copied the data in. So in actual fact, we were aware of this. We included the fact that the raw data did have pre-steady state in our processing. But if we had deleted this, if we didn't include this line and we actually had left in this time series that had these first couple of points, then this warning here would hopefully detect and tell us that we had pre-steady state. In this case, we took care of that in our processing, so it's not a problem. Great. But it's nice that the AFNI proc is looking out for us as much as it can. Additionally, when you acquire data, you're mapping signal to numerical values, and because the computer types have a finite amount of space on the computer they'll take up, they also have a finite range of numbers that they can store those values in. And the kind of saturation that's being talked about here would be if your time series included values that reached the maximum number storable. And if that happens, the danger is that the signal is actually going up higher than the numbers can record accurately. So that kind of saturation, in this case, means that you've reached a particular power of 2 minus 1, and so we can check for that. So it would be a particular case of data loss that the recordings from the scanner are missing out information potentially quite problematically. So it may just be one time point out of all of them, and maybe it's not problematic, but it could be a lot of them. So we'll try to flag that as a warning to check. In many cases, it's worth noting that when there's a warning that occurs, this is often something for you to check or double check and be sure about, even if there is a warning here, because these are automatic checks. Sometimes, for example, with pre-steady state warnings, sometimes it's actually just outliers due to motion that occurred during the first couple time points. And sometimes it really is due to pre-steady state. So this is just flagging something for you to check, and we're guessing at what it is. So anyways, it's worth noting that that level of interaction is still required. All right, so we don't have any saturation of our signal recorded values here, so that's good. The next warning that we have here is the left-right flip check. And this arises from a study that we had a few years ago now, where we noticed that in a lot of public data, there were cases where the EPI and the anatomical had a relative left-right flip between them. So maybe the anatomical was correct and converted from DICOMs, but when the EPI was converted, there was a left-right flip. So subject left now became subject right. That was relabeled incorrectly. So it's like one brain flipped in place. Now, if only we knew which one it was, that would be great. Often we don't, but what we can do is we can check and see if the sulcal and gyral patterns between the EPI and the anatomical look consistent. Now, there is often a little bit of distortion in the EPI data, but even given that, this is something we can check for automatically with our cost function. So basically, we align the EPI and anatomical as presented in the data, and then we flip one of them, the anatomical, and we try to do alignment, and we see whether the alignment looks particularly better in the first or second case, flipped or unflipped. What you really, really hope for, and what should be the case, is that the unflipped data matches better. And we show you both the, so here we don't find a warning. We show you the cost function values of what's happening, and with cost functions, actually, the better is more negative. So the original value of the cost function is a bigger negative number. So this means that this is a better matching as detected by the cost function. And we can not only just see the quantities, but get an image to verify them. So the EPI and anatomical, as I said, there might always be a little bit of distortion or some other things, but here we can see when we look in particular the upper cortex, which tends to have the most unique or subject-specific patterns to it, we see here that the red lines of the anatomical dataset edges really do match well with the ventricle outlines and the interior sulcal and gyral maps. We don't really focus as much, maybe surprisingly, on the boundaries because there's the distortion and also CSF, which is bright. Maybe skull stripping isn't perfect. We really focus on the inner gray matter boundaries. That's the fingerprint. Here, I mean, it's an alignment algorithm, so it tries to do what it can, and even the ventricles look pretty good. And so you might think like, well, maybe it is, but again, the hallmark signature of where left and right in humans are more individual and less symmetric is really up here, and it really looks like kind of a spaghetti mess versus here where it's tightly coupled in here. I'll note that for non-human data, this left-right flip check really doesn't work because, for example, macaque, marmoset, those non-human primates or rodent data, those brains are much more left-right symmetric. We can't tell them apart as well with this. So this is really for human data sets that we check it. But again, we found several public repositories where this was the case, and in other quality control projects that we've performed, we've found this again and again in many data sets. So it is a subtle thing, and I think many people weren't aware of this for a while, so this is why we check for it. All right, that's here. Now, one last thing that we check for is, again, something else that we've noticed in real data, and this is something that we call EPI variance lines. This was described in a particular quality control paper from the APQC project is where we first saw this and saw it systematically across data sets. The way we discovered it actually was using Instacore, but the hallmark that we can see of how we can check for it automatically is in raw EPI data. If you take the volumetric map and you calculate the variance at every location, and then you look at it, let's say sagittally, in some data sets, you'll find that there's just a bright, narrow column of high variance. Now, there's high variance around the edge because of subject motion. There may be high variance in the middle because of weaker signal strength. This is pretty common, but it's these very vertical features here, and they're highlighted by where this automatic detection program found them by these overlay kind of little red lines here showing the top and bottom. Now, it's worth noting that it's surprisingly difficult to check for it. These are very clear, but as you see, there are other things that have high variance, and sometimes like the edge of a brain can look like a vertical variance line, or the edge of the midline when the brain is rotated. So it's not, there can be some false positives found here. However, in this case, these are really hallmarks of this problem. Now, one way that we can see this is we can go to this location. So we start reporting here for each location that intersects across all runs. So the same XYZ location in the scanner space or run by run. And these are the XYZ locations. So what I want to do is I want to look at the raw data before any processing in its original space and go to this location and look at Instacore. And the way I can do that is, if you remember, we do actually have data that was just copied in without any processing. That was up in the RADcore block. And so now let's look at run 1, the Instacore there. Okay, so I copied that XYZ coordinate below, and now we have Instacore running. And if you remember what Instacore is, I'm going to hold down Control and Shift and click somewhere and see the correlation to that local spot. Well, now I have a particular XYZ location, so I'm going to right click before I do anything, and I am going to jump to the XYZ location that I copied from below, which was minus 2.7, minus 40, and 30. And let me just, I'll apply it and jump to that location. And now I can right click and say Instacore set to my current location. And if you notice, what do you see here? And this will be most particularly visible when you can see along the z-axis, the inferior superior, there's this correlation anti-correlation pattern, this kind of candy striping that we can see here. And now what I'm going to do is I'm going to hold down Control Shift, and I'm just going to move up along the inferior superior axis here, and you can see that there's this weird non-physiological pattern of correlation and anti-correlation. This is really a huge problem. Again, how did we get to this location? How did I know to click here? I knew about it by looking in the warns section, where here the EPI variance line warning told me it found a location here in run 1. So it's actually mostly the X and Y because it's a whole column. So this is just the kind of middle of it. And we could look for any of these around in these other locations as well and jump to them and try with Instacore. In reality, and actually with this data set, there are several variance lines. Often it appears when we see them, there's more than one. And so what we can look for is searching around. So now I was just looking for this vertical pattern as I move around. I'm in a different location and I just found another one. I could have gone to a location that the program told me, but so historically the way we found this was by using Instacore in process data and still seeing these weird patterns show up. So unfortunately, when we see these here in the raw data, processing really can't get rid of these. These are really ingrained as spatial temporal artifacts in the data. And so let me go to my VStat section now and click IC. So again, this is my fully processed data, and I'm going to look at the residuals that I have there. And now this is 450 time points. So Instacore is taking a little bit longer to get set up. But now as I move around in my data set, actually what I start seeing here, now that I kind of know what I'm looking for, I think I see this kind of pattern still stuck in my data of correlation, anti-correlation. And again, these are very kind of narrow columns of weirdness, but look at this. This is not something that is physiological. This is an artifact. And so there's a lot more we'll say about this in other discussions too, and looking at particularly resting state data where our entire analysis depends on spatial correlation. This is a spatial temporal correlation artifact injected into the data in many parts of the brain, and it's extended across a lot of the parts of the brain. And where we have more subject motion, it gets entwined with that, and it's really problematic. Probably any resting state data you see this in is maybe unusable. This is a question in task-based data. Now, we're not using correlation, we're using regression of this block design to see what's to see where significant responses are to our given task. Even so, it's highly problematic to have this strong structural spatial temporal artifact injected into the data. If you look and see where most of our analysis of interest is, it's going to be in the the visual and audio regions, because this is an audio-visual task. But there are parts of the brain we're going to be interested in across these networks elsewhere. And if I go back down to my warnings block here and look and see where I see artifact, well, I really do see them in a lot of different parts of the brain. Now, I'll also, this was the bottom of the warning section, and now you can see this medium level warning and how that's reflected here. If you remember from the very beginning of the start of our QC checks in the vorig section, we said that we have the original, just the data set itself for our min outlier data set. So this is our EPI time point that we use for volume registration. Below it now, what we've inserted here is a map of this scaled variance. The variance line artifact problem is actually so widespread and such a deep problem that we have put this here to have a searchable, navigable map of just the variance. And now, as you see, as I move through here, now you can recognize some of these very bright lines that appear here. And these are actually deeply problematic. So this is a way we can surf through, or I can surf through this way and clip and see a lot of them. But you can see in the frontal and inferior parts of the brain and here in the middle that these columns of strongly artifactual data appear throughout the volume. So again, what does this mean for my task-based data? For a block design, it might be a little bit less disruptive, and maybe it would be allowable to still use this data. For event-related data, it's really going to be a problem because the hallmark of this is strong variance patterns and similarity and anti-similarity through different, not even as simple as through different slices. It can really present in different ways and get tied in with motion. So this is really something that we'll emphasize again and again. You want to acquire pilot data, and you want to search for all the potential problems for what's causing potential issues, whether it's a task design in theory or in practice. Maybe the stimulus you're asking the subject to perform induces motion, or you have to have them practice more or something like that. Or maybe you have a scanner artifact that's occurring at the moment, which is something like this, and you have to deal with that with your MR physicists before you can really acquire a full study worth of data. But we'll repeat this again and again. You really have to look at your data as you process it. I don't really consider quality control and what we're looking at with our data here different than processing, because it feeds back into your study design, your data acquisition, all sorts of aspects of even other processing choices. You really have to look at your data, look at a lot of the checks that are here, think about skeptically what might be going wrong. We've really built up this list of checks and things by finding use for them again and again and again. These aren't just a large number of things that we've put together here. And anyways, this has been a longer, deeper dive through this in detail and kind of explaining everything. Normally, when I look at a given data set, I will go through and I will have a sense now of what I should be looking for in each case. And so hopefully this is something that you'll build up over time as you get more comfortable with these as well. So there we go. That is the warns section.